um, of the review from like last week. This is quickly a schedule. So it's like usual every other week. Today is February 3rd. Our next meeting will be on February 17th and so on. And then quickly, so just a quick review. Um, Last time we went over like an introduction to machine learning and more specifically image classification. So some of the terminology that we'll be using again and that you'll be seeing more frequently is like labels. So that's what we're trying to predict with our model. So we're trying to predict if your email is spam or not spam. And features, those are the variables that allow you to predict whether the email is spam or not spam. So essentially features could be stuff like the words, the address, the time, and there's a lot of features, right? You can imagine in a complicated project, there's going to be a lot of features. Then examples, that's like basically examples. They're the same thing as data. And there's two different types of data. There's the labeled examples. Just think of these as the data that we give the machine, the computer to train. So that's the stuff that where we mark the email as spam or not spam, then the computer learns from that. Then there's unlabeled examples. Those are ones where we use to test the model. So those are like new emails which haven't been labeled yet, and the computer goes and machine learning model goes and tries to label it. And a model is basically the algorithm that we are creating, and it has two phases: the training phase and the inference, or like the actual testing phase. And the training phase is where we like give it the data and it starts learning. And that's basically all you need to know for the terminology. And then image classification, some of the bigger issues we have were related to the semantic gap. This is just like a fancy word for like image issues. Um, it's just like big vocab. It's not too special. But essentially, like for example, if your viewpoint varies, if your camera moves around, then you're probably going to get a whole new picture with a bunch of different pixels, and that's an issue. Illumination, different lighting will also cause different pixel values, which is an issue. Similarly, deformation, occlusion, background clutter, intra-class variation, right? Like you have different types of species. Those are all issues with image classification that make it much more difficult for a computer to like predict what something is, because it doesn't like have a set number instead of like other forms of data, because images are a bunch of pixels in an array. Um, so we went over all of that last time, and to counter those challenges, we use a convolutional neural network, which I'm pretty sure we watched this video, and it just shows how the computer looks at the image more like a human does, and it has more filters and more layers, and by stacking those layers, it's able to detect what the actual image should be. And that's pretty much it for the review. So now we can get started with the more fun part. So this is Teachable Machine. Oh wait, also, if you wanted to view those articles, those files, uh, there's a link. And this is Teachable Machine. So if you can, it'd be great if you could follow along for this section. But I'm gonna have to turn off my camera, and you will see why soon. But essentially, this is created by Google. Um, and it's a project where it allows your computer to recognize, like as you can probably see here from the GIF, right? Like whether it's a machine learning model that can detect different types of like images, sounds, and poses, which are really just fancy images. And you can apply it in a lot of different ways. So in the bottom, I think it has some examples of like real life applications. So someone created like a little sorter, um, using facial gestures to trigger sounds. Someone used a teacher machine to turn their webcam into a game controller for Snake. That's pretty cool. Um, we probably won't be able to do stuff this advanced yet, but if you go to the website and click Get Started at the top, uh, it should take you to something like this, new project page, and you can choose out of the three options they have: image, audio, and pose. And pose really is just the same as image, except it's dealing with humans only, and it has like these dots and lines which signify your joints. So it's like if you only want to look at yourself, like an actual person, you might prefer the pose project over the image project. But for our purposes, we'll just do the image project because it's like more user friendly. We can use the image project for like a bunch of different things. When you click it, it will have this option standard or embedded. Um, just click standard and it should take you something like this. And so this is where you can start recording your data to create your model. So it automatically starts off with two different classes. You can edit the name of the class. So for example, first you kind of want to figure out what exactly you want your model to be able to do. So let's say one of the common examples is you want your model to like detect if a banana is ripe or unripe. So what you would need is you would first need at least one ripe banana and at least one unripe banana. And then you would label your first class as ripe and second class as unripe. I don't have bananas right now, but um, we can do something with like just regular facial and hand gestures. So I'll have the first class, we'll call it neutral. Then for add image samples, click webcam. And so this is where I have to turn off my camera and zoom because my computer won't let me open my webcam and the zoom camera. So hi. Basically, you can, it shows or your webcam is seen and you can click hold to record. And what that would do is it would start taking images and adding them to the data set for the neutral class. So if I hold the record and I kind of move around a bit, because like this is supposed to be neutral, and then it shows how many image samples I have. So after I release the hold button, it shows 156 image samples. And you can view all of them. You can delete some of them, like if one of them something went bad. But what I did here basically was we recorded some labeled examples for this neutral data set. And obviously it's called neutral because I'm not really doing anything. I'm just kind of standing. And the reason why um, you want to kind of move around when you do this is because it makes the model a bit like it allows it to learn a bit better, right? Because there's more variance in your data. If you only send it like the same image or the same like face or like the same frame for the whole time, it's not really going to have too much stuff to work with to actually like learn. And so you want to kind of have some more like variance here and there within your data set. And in class 2, um, we can do 5 fingers. So I'll hold up 5 fingers, right? And then so similarly, I click webcam. And then this time I'll hold up a 5 and move my hand around a bit. And so I'll have about like 150 image samples. You can have as many as you want. Obviously, the more image samples you have, the longer it will take to train your model. But it's normally not that big of a difference, like with time. It's only like a few seconds, really. So 150 is a good number. So we have a lot of pictures here. Move the hand around. So hopefully that should be good. And then we can actually just go and click train right now. And so um, this step is a bit longer. And yeah, you'll get the notification to not switch tabs because it needs to open to train it. Everything is web-based. So like you're not gonna get anything downloaded onto your computer when you like use the Teachable machine. And then the numbers there, like the 48 out of 50, will kind of, I'll talk about what those are later. But you see now, like I'm not really doing anything, I'm just talking, and it's showing the output neutral 100%. The percentage, as you might be able to tell, is like basically a certainty. It's like how certain is your model that this is the neutral class? And it's pretty certain because we trained the model pretty well. And I'm looking like very similar to the picture here. So if I hold up 5 fingers, you notice that it switches to the second class, the 5 fingers class, right? Because that's what the machine learning model is trained to recognize. And so you can switch back and forth. If I even go with my other hand, it also shows 10 fingers also. I wonder what happens if I go out of frame. So you see, it kind of goes a bit more crazier when Like it sees something that it's not really expecting, because it's either expecting a neutral like frame, which currently it is, or five fingers where you hold up five fingers. And so that's basically like a rough overview of how this works. But only having two classes is kind of simple. So we should add some more. And you'll see when we add some more classes, it gets a bit more complicated. So let's do like two fingers. Um, two fingers. And then let's also try three fingers. So obviously, the more classes you have and the more similar the classes are, the more difficult it is for the machine learning model to like be able to properly classify them. But there are ways around that. So three fingers. Okay. And then I'm gonna retrain the model. And so this time we have one, two, three, four classes. We have neutral class, the five fingers, the two fingers, and three fingers. Every time you add more data, you're gonna have to retrain the model. And this time, it should take a tiny bit longer. Oh, the page unresponsive, you can just click wait. It's pretty usual because like your computer's memory, if you're like me, is not that like capable. But you'll notice this time the training took a lot longer, or it's taking a lot longer. And we'll explain what the out of 50 is a bit later. But it's taking a lot longer because obviously there's a lot more data this time. Instead of just two classes, we have four classes. And okay, so it still shows neutral 100% certainty. So it's pretty nice. Five fingers. Oh, see, this time my right hand five fingers, it shows. So left hand five fingers, I think it's decently confident, kind of. Yeah. But right hand, for some reason, it's kind of viewing this as two fingers. But it kind of makes sense, right? Because when I train my model, I only use my left hand. And so it's not really expecting, like, it's not that used to the right hand, I guess. And then two fingers, it kind of works here and there. And then three fingers pretty much doesn't work. Oh, it kind of works. And so you notice, like, when adding a couple more classes, it becomes like a lot more difficult for the machine learning model to like recognize everything. So now you can kind of play around with the teachable machine yourself. It's pretty interesting, but and if you have any like issues or questions, you can like message or chat. But now let's take a look at like the advanced section. I actually don't know how to pronounce this. I think it's epochs. I forgot, but basically, um, one epoch is like an iteration or like a loop of your training. So, for example, um, you can read everything they have here, but in like a summary, it's the idea of like you give it data and the computer runs through all of this data how many times. So we told it to run through it 50 times, so 50 epochs, and basically it means it's getting loop through your entire data set 50 times. And the higher this number, so the higher the number 50, right? So if it's 100 or like 200, the more time it's going to take for the machine learning model to like train, because there's a lot more iterations it needs to run, but also the more accurate it will be. So if I were to up it to like 100 and retrain it, you should notice that the numbers here become like much more accurate. I'm not going to do that because it just takes a bit too much time, not really worth it. But you can play around with it at home, and you should notice that the higher this number goes, the better your model is because it trains a bit more. Batch size is not as important. Essentially, it's the idea like if I have, their example is pretty good. If you have 80, oh, oops. If you have 80 images and your batch size is 16, you're going to have five batches because 80 divided by 16 is equal to 5. And each batch like gets run by itself, then it counts as one epoch. Um, Batch size is not as important. And I also mentioned at the bottom that tweaking this number isn't really going to make too big of a difference. So like you would rather tweak your number of epochs instead of your batch size if you want to get like a better algorithm. And lastly is learning rate. So this one, they don't even explain it because it's pretty advanced. You'll notice like there's literally no explanation here, but you know, that's not a suitable explanation. So we're gonna kind of look into it, though it is gonna be, um, it's pretty advanced. So we're not gonna be able to go too in depth or understand it too well. But it deals with the idea of gradient descent, which is um, it's like this idea within mathematics, and specifically, it deals with like calculus and derivatives, which none of us have really learned, I don't think. But essentially, um, this is a nice website. Uh, we can skip all of the introduction because it's a bit out of our scope, our range. But the idea of gradient descent is that with our machine learning model, we have a bunch of different features, right? Input variables. The features and input variables are not listed. There's no like list of features. The machine learning model comes up with that list basically by itself. Some examples of the features like could be the lighting, the number of fingers I hold up, my facial expression, all of that could be considered features, right? And the machine learning model has to determine which of those features are useful and which of the features are not useful, right? So hopefully if the model is good, it should determine that my facial expression is not that important because in this example, we're only looking at the number of fingers I'm holding up. So hopefully it understands that the feature relating to the number of joints or like, fingers in the air is much more important than what my face is looking like or what the lighting is looking like, because those are not relevant to what our goal is. And so that's what the features portion of it is. So you can think of the features as variables, right? And when you have variables, you can graph your variables and you can give it like a function. So let's say, for example, I have just 5 features and each feature is one finger, right? So I have 5 fingers, 5 features, 5 variables. And when you graph this 5 variable equation, you can think about it as like, actually, never mind, just scrap that. But basically, you're graphing like this equation and it has like 5 input variables or whatever. And you're going to end up with some sort of graph that looks something like this, something like this. Um, don't worry about any of the text. I don't even understand what it means. But you're going to end up with like a 3-dimensional graph that has a lot of contours. And the goal that the machine learning model wants to do is it wants to reach the lowest portion on this graph. So as you can see here, ignore the saddle point. We're not going to talk about that. But there is a global minimum, right? So the shortest, the smallest point on this graph is clearly right here at 1.5, right? And that's where your machine learning model wants to arrive to. But how does that work? Like with our images, basically once it arrives at that minimum, that's like the most optimal point for all of your variables. If I have 5 variables, each of these variables has like a constant in front of it or like a weight. So each of them has a weight. So for example, like my facial expression, that variable in front of it has a weight. You can think about the weight from like 0 to 1, right? With 0 being the smallest and 1 being the most important. And hopefully the weight for my facial expression is very small, like 0 or 0.1 or 0.001, right? Because we don't want to account for that. But hopefully the weight for my fingers are much higher, like 1 or 0.99 or 0.9999, right? Because that's more important to what we're trying to do. And so once it reaches that minimum part, that global minimum, that's essentially where all of your features, the weights for all of your variables are at its best possible scenario. So like it's the most optimal it can be. And the learning rate and the way the gradient descent algorithm works is it randomly chooses a point on your graph. So let's say it chooses this point here to start, and it just slowly goes down in increments until it reaches a point where it finds that it can't reach any lower. And that's roughly how it works. There's a better, so here. So if we have a simple graph like a parabola, I'm sure we all know what a parabola is, right? Y equals x squared. Let's say you chose your random, oh, you can zoom in? Wait, what? Oh, that's crazy. Okay, so imagine you chose your first point here, right? That's your like 0th step or whatever. So that's where you're starting from. Then your next step, you would reach 1, 2, 3, 4. And each step you'll get smaller and smaller, right? The distance, because it's an exponential, parabola function. And soon, once it gets super, super small, you're going to realize that, hey, I finally reached my global minimum, the very bottom part, which is the goal of gradient descent. And once it reaches there, your job is done. The machine learning is done. You can actually start running it and like testing it. And the learning rate is the distance between each descent downwards. So here on the left, the learning rate is 0.1, which means the x direction, or the difference in the x-axis between each point is 0.1. So from 0 to 1, it moves 0.1 units to the left. From 1 to 2, it moves 0.1 units to the left. From 2 to 3, it moves another 0.1 units to the left, and so on. But on the right, the learning rate is 0.8, which means from 0 to 1, it moves 0.8 units to the left. So you can see this distance is like much larger in comparison to this one. And so this is a bad learning rate, because you see that your path is zigzag, which is not good. Because when you have a more complicated graph, you're likely to overshoot your global minimum, or you won't reach your global minimum in time. So if your learning rate is too small, like 0.000000001, which is really, really small, right? Each movement to the left is going to be just a tiny, tiny difference. And it's going to take you like years to reach your global minimum, which is not good. But if your learning rate is too high, like 0.8 or 0.9 or whatever, you're likely going to overshoot your global minimum, because each time you get closer down, you're going to be going too far in the opposite direction. And sometimes, if you're lucky, you'll still be able to end up at the correct point, but most of the time, it's not recommended. And so that's why the global minimum that we have, or the learning rate, sorry, is 0.001. And that's also why they recommend you not to tweak it, because it's kind of bad. So like, for example, we can try something. I'm gonna put it to 0.1 and train the model, and we'll see how much worse it is. In the meantime, if anyone has any questions, now is the time. But you also notice that it is, I'm not sure. Is it faster than last time? But after this, we can try like 0.00001. And if, our theory is correct, it should take a very, very long time. Okay, so you see, immediately, this is my neutral phase, right? Like, I'm not doing anything, and it's showing 3 fingers 100%, which is like pretty off. And that's because our learning rate is 0.1. So we can still try everything else, like 5 fingers. Oh, okay, no difference at all. Wow. Huh. And well, I was hoping it would at least like differ a tiny bit, but I think 0.1 might have been a bit too overboard. But you can hopefully that kind of illustrates like the how the learning rate works. You don't want it too high, because once it's too high, it's going to be extremely inaccurate. And so now let's try a lot of okay, is that the minimum? So that's 0.0, that's 0.1, or that's 1 times 10 to the negative 7, which is 0.00000001 with like 6 zeros in front of it, I think. But this time, if we're correct, the training should take a lot longer. Why is it not taking longer? The learning rate isn't small enough, I think. But gradient descent it's a pretty advanced topic, actually. So if you don't understand it, that's completely fine. It's like I think it's almost college level. Okay, let's try. So, oh wow, it's very interesting. So it has percentages for all four. So it's right now it thinks 20% certain that it's a neutral phase, 20% certain is 5 fingers, 30% is 2 fingers, and 25% 3 fingers. We're gonna try 5 fingers. It kind of thinks it's more neutral now. 2 fingers, 3 fingers. Anyways, once again, you'll see that, with the learning rate too small, our machine learning model doesn't work either. I don't know what's going on here, but clearly it's not working. So that's why the learning rate is important to keep it somewhere like not too big, not too small. So whatever they had as their default 0.001 was pretty perfect, as it actually worked in comparison to these values. Oh, uh, I think I clicked stop training. Okay, well, anyways, there's also moving on. There's also one more thing. It's called under the hood. This is like even more advanced stuff. So they do have some vocab sections, all of this stuff, but most of it we kind of know. Underfit and overfit. It kind of has something to do with the gradient descent I was talking about. Essentially, you're trying to find a line of best fit. If you've ever seen, let me find an image. There's like this really popular image I think most people have kind of seen before. But so in machine learning, underfit, overfit, um, if I can't find it. But all right, so the example that most people use is if you're trying to identify cancer and there's benign and malign. That's definitely not how you pronounce it. But there's the bad cancer and there's the cancer that's harmless, essentially. And so that's like two different variables. And you plot them on the same graph, X's and O's, right? So you can differentiate them. And what you want to do is you want to create a line that circles the O's and keeps the X's out, if that makes sense. So like here, the appropriate fitting, you'll see the line, right? It kind of, encloses the O's and X closes the X's. Um, and that line is kind of like your threshold. If it's past this line, then it must be an X. If it's past the line on the other side, it must be an O. And underfitting on the left is where it's too simple to explain a variance, or basically the line does not fit at all, right? Like it's not accurate here. The straight line would not do for this example. And overfitting is where you train it too much. And so the overfitting is kind of an example where we use the learning rate of 10 to the negative 7, like the super, super small learning rate. It's trying too hard to get a perfect fit. And so you can see the line is like really, really, really squiggled because it's trying really hard to only get the correct classifications, which is not what we want either. Because, sometimes there are a few outliers here and there, which is totally normal. There's nothing you can do about that. It's just how it works. And you don't want your line of best fit to like be overfit either. And underfit would be more like when we tried the learning rate of 0.1 and where it was super, super inaccurate. And that's kind of more underfit. And so that's what the section is talking about. And then they also have accuracy per class, and you can calculate this. It's pretty self-explanatory is how accurate each class is. We're not going to do it because it takes some time. Don't worry about this confusion matrix. And the accuracy per epoch and is it's part of the accuracy per class idea. And same with the loss per epoch. You can read all of this here and here, but this is some more advanced concepts that we're not really going to be talking about. And that's pretty much it. You can save your project once you're done. You can save it to Drive, or you can also download it. And if you are like interested in trying to like implement this in your own code, or like you have like a project working on and you know how to do it, then you would export your model here. And it gives you a lot of different options on how you can add this into like JavaScript, TensorFlow, and Python, and all of that stuff, which is pretty nice. We're not going to be doing any of that because it's beyond our scope here today. So yeah, if anyone has any questions, now's the time. Otherwise, we'll see everyone in 2 weeks, and we'll shift from machine learning and talk a bit more about artificial intelligence next time.